in Y area. All right? Y area does this one. All right? Try to make noise. How does it do? He say his pre-response are, all right? You have an X, B, I, Z, Z, top down Pi equals to, now, if you remember we used the, last time we talked about inner product, right? So talked about the X hat, make it a unit vector, then inner product with Bi hat, that's unit vector. Unit vector, unit vector. Before we are doing this one, but now we have two parts. Not just bottom-up part, but also top-down part. So with top-down part, we say add the Z part hat inner product with my feature T I. If this maximum, last time we said maximum is 1, right? This is maximum 1, and together will be 2. So let's do a half thing. All right? Maybe do it this way. Easier way is just half here, half, and a half. So now, if you do that, the best value, the highest value you can get for pre-response is 1. This is 1 to minus 1. This is 1 to minus 1. The highest one is 1 because you have half. So it's like 50% of energy from bottom-up way match. 50% of energy from top-down way. So you get 50% from Q match, all right? 50% from sigma match. If I match, it's like, haha, I found that cell. All right, if match well. But right now you do not have label right now. All right, if you do not have label, then how do you know? How do you make noise? This is the noise you make. All right, you make noise because there's no government. All right, you just have cell, you make noise. Then how do you know? You compete with others. All right, you compete with us. Competition goes on. I give the I. Say, how many neurons we have? Say I equals 7. So I equals 1, 2, 7. All right, we have 7 neurons. 7 neurons, every neuron compute. Then, En computes, they call it emergent. Emergent function, all right? What it does is that you want to find J, this is called competition arc max for the 17 of say. Okay, 7, right? And you find the pre-response that has highest match. This is bottom up, top down. And add together means, oh, I get best match, then a voice is louder, all right? This is louder, and the argument of the max of the pre-response becomes J. Say J response the highest. So we are lucky if we say this is the highest, all right? This is the highest and others lower. If that's the case, then we want to make this one, this neuron to 5. So Y response, because you are the best match, you are the expert. Yj equal to 1, all right? So this one becomes 1, all others become zeros, all right? Others are not expert. Don't make noise because you are not good enough, not expert, all right? In fact, not good expert is actually good because it's a long-term memory. Long-term memory don't make noise. And this is expert, he can improve, right? But those guys are not expert, don't make noise, don't update your memory. Why? Because this is long-term memory. Those guys are features for other cases. Current case is not your business. Don't mess around with that. Otherwise you lose your memory, all right? So now this yi equal to 1, then yj equal to 1 because it's expert, so you get a full voice. After computing, you get full voice. And this guy, Other guys do not get noise. I equal 1, 2, 8. I'm sorry, 7. Okay, 7. Sorry. All right. Of course, you have in the brain. This number is big. All right. Brain you have 100 billion neurons. 100 billion. All right. 100 billion compete, and whoever win and start to make noise. All right. So this one is making noise right now. All right. Now, so what's making noise? What happens? In FA, right? FA in the diagram like this. I have a state Q, then I have a sigma gets in there, and I have to transit the new state of the Q prime, right? And in the diagram, as Q and sigma will find this Q and sigma find that entry. The entry goes where you don't know yet. So this arrow is actually found by this neuron. That neuron makes noise because I have the best match, all right? But next state Q prime is not this business. Basically, I have the best match. But where this state goes, I don't know. I just make noise, all right? The next state will be rely on this computation, all right? So I'll show you how it is. Maybe I need to go to here again and redraw the simpler diagram and see how it happens, all right? So now you know that the entry in the table, but you don't know what kind of state you need to fill in. And that state is also a pattern. Right now we do not have a symbol in the network, not in your brain, all right? So DM will first compute that one, the X, Y, equal to Z, and this is how neuron compute. That Y neuron 5, and this is 1, and others are suppressed. So you have an X, T, you have Z, T is the time, all right? Then Y, T plus 1, will try to find a match, all right, match this one. In other words, match of a Q with sigma, basically, in the symbol version. Symbol is a Q and sigma. And this is a pattern, this is a pattern. So now we need the inner product, all right? It's not a pattern, we don't need the inner product. Now we need it, all right? So this one starts to make noise. This is 1, others are 0, 0, 0. This is 1, 0, 0, 0. All right, this is 1. Then next, what do we do? Next is that I have a network, the same network. All right, the network, this one is 1, right? 0, 0, 0, 0, 0, 0. What do I do? Every pixel over here start to use that one in time vector as input. This is connected. And this network will predict the response here. 0 will not give any contribution, but this one make noise, all right? So this one will predict what value over here in this pixel. And every pixel actually will do the same thing, all right? Every pixel will be predicted. And that's why do we need to predict pixel? Think about it, you are watching a video, right? If you freeze it, it looks noisy, right? If you let it go, it's noisy again. Why? Because your brain is really predicting next images, all right? You predict, once you predict with the image and you predict, you reduce noise. Noise is kind of random, not predictable. So you reduce the noise, all right? So in fact, your brain is predicting image, and your brain is also predicting what? Your action, all right? So you see, you have a touchdown football, and you say, you start to, that's your action, all right? That action is predicted over here, all right? And every neuron is predicting here. Right? I call it neuron. Actually, it's just a node. All right, it's a node. Then what it does? Right. Over here you have t plus 1, right? Y t plus 1. That matched, good match of q and sigma, right? Then this one is giving you the sigma prime, means that what's the next? I should do t plus 2, why? This is t plus 1. And you have another unit, a network updating in t plus 2, and this one is q prime corresponding to z t plus 2. Right? So now this is a network that produces transition T. I summarize how that can happen, right? Originally, you have sigma and a cube, that's symbol. Symbol will not be emergent. You will not have a symbol from real world, right? And you have images, which is a pattern, and images of your muscle firing, right? Then pattern can be from real world, all right? Not symbols. Symbols is something that human invented for communication between humans. Then this neuron will match the pattern. So this is the best match, start to fire. So, oh, I'm the best match. I know what's going on in X. What's going on in Y, basically. All right? Then once it's fired, then this guy start to be heard by the next time. Next time that every connection will be here, will predict the image in the X, also predict image in Z. And the image in Z is your action, your claps. Right? That's your action. Now think about it. How do you teach? I'm finished. What do we do actually? Let me see. So how do we do this one? I need to write a Z, all right? Z computes. Use the same equation we have here, all right? Z compute in the product too. Z computes J equals arg max. I equal to how many do you know? 1, 2, 3, 4, 5, 6. See, 6. Of course, in the muscle you have millions of muscles, all right? Then you do response, right? The pre-response of input is Y now, all right? Because this one takes Y as input, all right? Y, and you have the BI. BI is the for this neuron, you have this one called BI. I equal to 1, 2, 3, 4, 5, 6. BI, all right? Now it does not have a top-down match. It just has a bottom-up match. Now you end up with this one equals to the goodness match from the Y to the bottom-up match, all right? Then the Z response is that ZJ equals to 1 because the winner, all right, I write it here, that Zj equals to 1 or Zi equals to 0 for all the components that I equals not equal to J. I equals to 1, 2, 3, 4, 5, 6. Then you say, how this pattern is correct? How do you know that if I do this from the winner, whoever the winner, then you find this to be the correct. Then into the little analysis, that gives you the reason why we're correct. If the pattern, if we do this one, all right, assuming that every here have only one neuron firing for every Z pattern. In other words, you only have one muscle is firing. So this is the one muscle. This is another muscle. All right? This is the simplest version. Otherwise, you cannot use the one winner. All right? And if that's the case, you have one neuron firing every single time, then this is the winner, and the winner he get a lot of good match over here, then it becomes 1, other becomes 0, and think about it, all right? If this one fire, and the next one is this one fire, then because the learning equation we had, this connection will be established. Actually, computation will show that this. I will show next time. Next, how the updated function will establish link, and this link is just numerical computational linked from here to here. So next time, if you will the winner, I guarantee will fire. Think about it, all right? Because this one will not connected to this. This will become 0. This will not be connected. This will become 0 when it's always this fire. When this guy has energy, right? But if this one connected to me, I will fire. And this one, they're not connected. This one, this is no way to have an energy to fire. And this one doesn't. So I only the only neuron fire, and it must be the correct one, right? Because last time you fired, and after that I fired, because teacher teach me this fire, then this link will be established. How do we establish this correct link? Without going to over there, other places. That's what we call it update function. All right, so write down update function. An update function is very simple. That's what the brain does, the cell does. All right, it's called Hebrew learning. Don't worry about it. Don't worry about it. I probably ought to say that. It's called Hebrew wait. Update. Every neuron, if you win, it does it. It does the same thing. All right. So Y is the W is the vector. This is retention rate. This is the old vector, old weight vector. This is the learning rate, and this is the response of the neuron is 1. This is the multiplication. Then for Y, it has 2 inputs, WT, 0. All right, you can see that. So I have a bottom up, top down, and the sensory is this N. What is N? N is the number of neuron. N is the final age. Number of times that neuron fires. Y neuron. Alright? You can see that the more time you fire, the larger the value, then the learning rate becomes lower. This means that your father will not learn as fast as you, because his brain is not very plastic. And you are more plastic, but you're still young. Because that number for you is smaller, and your father's number will be larger. And this is the retention rate, and this is the learning rate, and add together equal to 1. You see that? Add together equal to 1, so you end up with a new weight. That new weight, you think about it, all right? You think about if this is 0, 1 on it, all right, 0, 1, and then if you have 0, 1 over here, if that's the connection pattern, and it will update. We'll update it. And for Z, we do the same thing, except that it doesn't have the top-down invert. If this is a firing neuron, right? If it didn't fire, you will not have update. You do not update. Then you have YT. The YT is the pattern over here, all right? We get this one. So this is actually the same updated function for the input, updated neuron connections, all right? Now I will not prove it, all right? But you need to see that actually what this equation is incremental of computation of the average of this vector. This vector in the history, if the fire to say 10 times, and I get 10 of this one, get average. And this one, the same thing, all right, average. Now, if we can learn in a way so that every time I become winner, you get exact vector, then average does not change it, right? If I have 10 vectors, they're exactly the same, you have average 10 times, you still get that vector. So the next I will explain it, if this network, using this equation, to learn FA, then the network weight never change after initialization. All right, because of the same vector, same Q sigma vector. I average, you still get the same vector, so my match is always perfect. That's why you can have no error. All right. Now, I want to propose something that how the En learns FA. Why do you do that? So think about FA is the not common sense knowledge of your parents. your father, your mother, and your school teachers. All right? So FA, a huge ontology or common sense knowledge. All right? The FA, when it runs, only give you two pairs. Sigma is input, and the Q is the state. So only produce this one. All right. Then I have Dn. Dn is looking at the input-output pair of your module. It's doing something. All right. So this is for X. Your mother's input, and this is your mother's action. Your mother's action is for your Z action. If you can simulate your mother's input and output, think about it. This is your mother's input. This is your mother's output. If you simulate, if I can learn that Dn, then you learn your mother's common sense knowledge. Then after your father got back, you start to observe your father's input and output pair. Then you get your father's common sense knowledge. Right? Now, next I will show that you will not have error. All right? You are a perfect learner. Right? The reason that it can be perfect is because this FA has a finite number of input and output, all right? And your match is perfect. And in reality, it's not the case, all right? So let's see that. So now learns FA, all right? So Dn observe FA operations through state Q and sigma. All right? And this Dn need to generate neurons because the way with baby time you do not have enough neurons, right? And you generate more neurons. So if the Y neuron max of this neuron of the match are X, BI, Z, TI, it's not perfect. Perfect means less than 1. It's not perfect, all right? This means that you have input pair that's not equal to your weight vector. Then what do? You want to generate a new neuron, all right? Then you create, assuming that you can create a new Y neuron, all right, and initialize it. Its weight vector. The bottom up is the input. Top down is the Z input. All right. So that one is your corresponding to the sigma, and Z is corresponding to the Q. So in other words, that this new neuron was initialized by the exact bottom-up input and the exact top-down input. So this weight is perfect, right? So then it computes. Aha! I'm new. I get perfect match. Then I start to make noise, right? Others will not be perfect, right? So I start to make noise because I'm finding 1. Then your matching is correct, all right? So in other words, like in the FA, you have Q, sigma, with Q prime, and this one was not there. Originally it was not there. There is like Q double prime was there, Q prime not there, and this one not there. And Y neuron was created new, so it started to make noise. All right. Then next Z will be supervised by this vector. All right. Of course, this is a symbol, but in reality, it clapped. All right. And your muscle firing pattern becomes an image and will be learned that this new Y neuron perfectly matches X and Z and is the winner in Y. It might be the winner, all right? Then the next time, the Z neuron will fire. Z was taught to find the Q prime pattern. All right? Because this is a new created, then it will find a new pattern. In other words, we get to theory, all right? Very interesting. That you can have a network that running on mathematics, just like that, all right? Can simulate your father, mother's FA through your X and Z, and in general Y, it's perfect if you have enough neurons, if your brain is big enough, in other words, right? Now, FA, you have a finite number of transitions, right? And a finite number of symbols, so you do not need infinite large network. You just have a finite bounded number, all right? So the theorist said that, the student said that way. The developmental network learns any complex FA ontology, all right? This is like ontology, common sense ontology, you know. Common sense knowledge of human, all right? Incrementally, from its observations of the FA operations. Right? And interestingly that this Dn never make any error. Because alpha Z is always taught in the right time. After learning each transition. Because you have sufficient neurons to generate and memorize this case, all right? And the match is perfect. The next time Z is learning is learned is correct. So there's no error. Then this network, the Dn, generalize to all state equivalent, because later on you have new sequences, but as long as they're equivalent sequences, it generalizes perfectly. It's like we have FA, right? We have sequence. And that sequence, new sequence, is never observed, but the FA can accept it because the transition was there, and it will give the acceptance. In this case, it's like you have a new case that your mother never taught you because of sequence, all right? But it's a state equivalent. I'll give you an example. Say this is black, and this is black, all right? And this villain, this is black, this is black. They get something new, like this, all right? You know this is black. So as long as you understand the black, then this black concept becomes a state. That state allows you to generalize using this black state as a context for new sequences. And you do not have error. You do not have error. Your mom does not need to tell you, oh, this is also black, all right? Because you know it's black, and this black concept can be used in the new setting, all right? New setting. So now it's very interesting. We'll get to the end of our conclusion, all right? So FA is a huge ontology. Big human common sense knowledge, all right? Then DN, think about it, it simulates a charge where it's not everything yet, it's only very basic theory said that if can simulate a child brain, then what happens? This means that a child can learn from experience, from the FA experience, all right? Perfectly, as long as your brain is large enough, because FA is a finite size, all right? In fact, number of cells you need from the Y area, number of cells you need, or number of neurons you need, is equal to number of transitions in the FA, all right? It's bounded. Number of transitions. The next one is even more interesting, all right? Now, so this child learned a common sense knowledge from the FA, right? What if let the child go to the real world? How does it perform? It performs optimally. All right, I'll write it down. If the DN is exposed to the infinite many inputs of the real world, all right? In terms of the images and the actions, all right? The DN, the child brain, a simplified version, DN is optimal in the sense of maximum likelihood. If you've taken probability, all right? Maximum likelihood means that it gives the best guess, or better thinking. In fact, the thinking is also modeled in that way. So you are thinking in an optimal way. But you say, why we have different brain and think differently? This is because environment is different. All right? Give example, if you get bullied when you're in the primary school and you hate school, you don't go to school, then you have a bad environment. All right? So everybody's experience is different. And brain mechanisms are very similar. If this is the only mechanism we are talking about, of course, not the only mechanism, all right? There are other things, all right? But if the only mechanism we are talking about, then this model basically is that the reason that different brains perform differently is because the environment is different. Everybody's family different, your friends are different, your parents are different, and some parents are more motivated and teach you, hey guys, you have bright future. Then you will be more doing something exciting. All right? Yes.
What about like opinion? Also, can it change with opinion, like environment also? But couldn't you have two things from the same environment, but they could have different outputs just based on?
You see, opinion, right?
Yeah.
All right. The Sam was raising a very good question. He said that if that's the case, then can you change your opinion? It does. All right, it does. We talked about the Boston bombing, all right? And those guys was in a different environment, All right, I guess that they get different environment raised up, and have the different buddies. You know, they have brothers, right? They have brothers. They say, "Oh, this is bad." You say, "Yes, really bad." Then let's do something about it. All right, and did not get the correct information. You know, give example that that the environment could be very skewed, right? When it's skewed, then they start to do things that really that not the best for them. Right now, you can see that one guy got killed, right? Another was seriously injured, right? So in this case, that this kind of formulation could be potentially useful for us to understand how the brain works, right? And what we can do. You know, my view is that really no brain is bad. Brain is never bad. It's the environment, all right? And the environment did not provide the correct information to the brain, and brain start to do something that's not really best for the body, for the person, all right? And the Boston bombing is an example. All right, example. Good question. And I'm not trying to answer every question, but these questions related. All right. Other questions? More questions? All right. Thank you very much. And this is not an exam. All right. I just give you something that could be useful potentially. In other words, you can write a program right now. All right. If you are interested, there are some article that I'll probably give you one article that you can write, you can read. The article is by me, all right? The title is that, why have we passed the neural, I go to there, neural works not as checked. Wow. And we know neural networks has a history at least as long as traditional AI, right? Because even Turing's time, he already knows the connection of the neurons, right? But turns out that we do not have a theory that can relate network to logic. Right now, our logic is based on FA, and we also have a probability version, right? Probability version is the optimal, right? It turns out the weight is the probability, right, based on the formulation. So if you're interested, you can read that. You can probably just do a Google search. It's also available on my network, all right? We have an optimal brain model. We can learn from the real world, from physics. In fact, that network programs itself, right? It does not need to hand design the FA. Your parents, your teacher have FA, and learn from your parents, teacher, and buddies, and you learn in an optimal way. And that's why you can have example, right? This is a chart. The next time you see a chart, you do not make errors. When you have infinite many inputs, then you start to make errors because the brain has a finite size, right? So that's, but still optimal. That's still optimal, right?